Have you ever tried surfing? In order to surf, we need waves. However, a surfer doesn't want to ride just any wave. Surfers want to catch waves that are nice and big or which have a high amplitude. Also, it wouldn't be any fun if a wave appears and disappears quickly. Surfers like waves that last long or those with a long wavelength and wave period. This illustration shows us a simple sine wave. You'll see patterns like it in sound waves, microwaves, and yes, even ocean waves. Like all waves, it has crests or peaks, which are the highest points. It also has troughs, the lowest points. The wavelength of this wave is the distance between one of its peaks and the next peak. Wavelength is represented by the Greek letter lambda. You might notice that the distance between peaks is the same as the distance between troughs. We can also measure wavelength from one trough to the next. Either way, the wavelength will measure the distance of one wave cycle, or one completion of the waves repeating up and down pattern. The wave period is the measure of time it takes for the wave cycle to complete. We usually measure the wave period in seconds and represent it with the letter T. Before we find the period of a wave, it helps to know the frequency of the wave. That is the number of times the wave cycle repeats in a given time period. This graph shows us 5 different waves with different frequencies. You can see that each wave has a different amount of cycles over the same period of time. We could find the exact number by counting the peaks or troughs. The red wave has the lowest frequency among the 5 because it has the least number of repeating cycles. And the pink wave has the highest frequency because it has the highest number of repeating cycles. Frequency can be obtained by dividing the wave's velocity, usually symbolized by the letter v, by its wavelength. Remember, we represent it with the Greek symbol lambda. We usually measure the wavelength in meters and the velocity in meters per second. The frequency found using these units will be measured in hertz. Another way of saying cycles per second. Let's say we determine a wave moves at 60 hertz. That wave will have 60 cycles per second. When writing formulas, hertz is usually abbreviated to Hz. So how can knowing the frequency help us find a wave period? The higher the frequency of a wave, the lower the wave period. After all, if you're going to fit more cycles into a certain period of time, the cycles need to be shorter. We can say that the frequency and wave period are inversely proportional to each other. So if the frequency increases, the period decreases and vice versa. In other words, if the frequency is large, then the period is short. And if the frequency is small, then the period is long. Remember that wavelength and velocity both affect a wave's frequency, so we can also say that the higher the wavelength, the higher the wave period, and the lower the velocity, the higher the wave period. The wave period is actually the reciprocal of the frequency, which means that any wave will have a wave period of 1 over the wave's frequency. The standard unit for period is in seconds, abbreviated as the letter S. Let's do a little bit of practice. Here's a word problem. You're on vacation at the beach and it's a windy day. While looking at the ocean waves, you observe that the approximate velocity of a wave is 3 meters per second, and the distance between the peaks of 2 waves is approximately 20 meters. What are the frequency and wave period for these waves? Okay, we know the velocity, which is 3 meters per second. We also know the wavelength. Remember, that's the distance between 2 peaks. So we call the wavelength 20 meters. We can use these 2 bits of information to find the frequency. Divide the velocity, 3 meters per second, find the wavelength, 20 meters, and we find that the frequency is 0.15 hertz, or 0.15 cycles per second. Then we find the reciprocal of that number. 1 over 0.15 will give us a value of 6.67. That tells us that the wave period is 6.67 seconds. Here's another. The color red has a frequency of 4 times 10 to the 14th hertz, and the color violet has a frequency of 8 times 10 to the 14th hertz. What are the wave periods for the 2 colors? Which color has a higher wave period? This one is easy because we already know the frequencies of the waves we're looking at. All we need to do is find the reciprocal of each frequency. The reciprocal of 4 times 10 to the 14th power is 2.5 times 10 to the negative 15th, which means that the color red's wave period will be 2.5 times 10 to the negative 15th seconds. Violet's reciprocal, and therefore its wave period, is 1.25 times 10 to the negative 15th seconds. These are complicated numbers, but we can still answer the second question. Which color has a higher wave period? In this case, the answer is red, whose wave cycle is just a bit slower. We can also figure this out given the frequencies of the two waves. Remember that frequency is inversely proportional to wave period. That means the higher the frequency of a wave, the smaller its wave period will be. Violet waves have a higher frequency than red waves. That means that we know that red waves will have higher wave periods than violet waves without having to plug it into any equations. Every day, we encounter waves. Sometimes we see them when we go to the beach and look at the ocean. Other times they are invisible, such as the waves in microwaves and radio waves. Different waves have different frequencies and periods. The wave period is the time it takes a wave to complete one cycle. The standard unit of a wave period is in seconds, and it is inversely proportional to the frequency of a wave, which is the number of cycles of waves that occur in 1 second. In other words, the higher the frequency of a wave, the lower the wave period. The wave period is also dependent on the wavelength and the velocity. The higher the velocity, the lower the wave period, and the higher the wavelength, the higher the wave period.